In the last class, we had started discussing about image enhancement. So we just towards the last we spent some time. I'll just briefly review that and continue there. So we are basically going to discuss spatial domain enhancement techniques. There are some frequency domain techniques also that we'll probably discuss later on because we need to first explain what is frequency and what is spatial domain. Spatial domain is the normal, basically, when we are representing images in spatial domain in the sense in x and y axis, that is called spatial domain. We can transform that image in frequency. We can try to extract some frequency components, and then we can do some other set of operations in the frequency domain. So for that, we will discuss later on what is frequency, what do you mean by frequency in images, and so on. But for now, we are going to talk only about spatial domain things. So we'll be basically discussing three categories or three broad. This was just one classification. We'll discuss point processing operations, histogram based operations, and neighborhood operations. So as I said yesterday, enhancement can be done for either for improving the contrast or highlighting some particular details in an image which may not be visible, or for removing noise, or just to make it more visually appealing. And these are some examples here. For example, this is a medical image of a bone x-ray somewhere, or I don't know. So the contrast is not so good, so you can actually try to, I don't know whether it is visible here, uh, but at least some more details are visible here as compared to this image here. This is another image where the gray levels have been stretched in order to see some more detail in the image. And this is an example of suppressing noise. If the image is corrupted by some random Gaussian noise, we can do some enhancement techniques by which we can remove noise. And this just to make the image more smoother and more appealing. So it's just trying to do some smoothing effect here. So here we'll be using some kind of a transformation operator on the input image F to get an enhanced image G. This transformation operator is slightly different than what we discussed in the previous class when we were trying to transform an image geometrically. So there the transformation was being applied directly on the x and y values itself. The x and y value itself were being transformed to some other values. Here we are not going to touch these xy values. We are only going to touch the intensity values at those xy locations and change only the intensity, transform only the intensity values. So the transform operator, this transformation operator may be defined over either just over that pixel itself or over some neighborhood of that pixel. So for now, we are only going to consider that particular pixel, not the neighborhood of that pixel. So when we are only going to consider just that pixel, then it's called point processing operations or simple gray level transformation functions. So that transformation function, then we don't, there is no x and y now involved here. So we will be just taking some particular intensity value r in the input range and mapping it to some intensity value s in the output range. So that will be t will be a simple mapping function which will map value from an input intensity value r to an output intensity value s. And this is the example we discussed last class. So this example is basically where the first transformation function or the mapping function can be seen as a contrast stretching function. So as we discussed in the let us say on x-axis we have your input range r, input variable r, and output is on your y-axis s, and this is your transformation function tr. So let us say this is your identity SL to R. So as we can see, So it is not just simply if we just simply multiply all the values by some factor, it is going to uniformly increase all intensity values or decrease intensity values. If we take a factor greater than 1, it will brighten the image. Or if we take factor smaller than 1, it will darken the image. So but all the intensity values will be changed by an equivalent factor. But here, as you can see, intensity values less than k, they are all being shifted towards the darker side, and intensity values greater than k are being shifted up towards the brighter side. And the most important thing that is happening is here is that the values between, let us say, r1 and r2, values less than r1, they are all being mapped close to 0, and values greater than r2 are being mapped close to the highest intensity level. And the values between r1 and r2, they are now being actually occupying the entire range. So basically this will be a good transformation function if your input image has most of the intensity values distributed between r1 and r2. Then you can just stretch that contrast so that all the intensity values can be, all the intensity levels could be used. So this transformation function in an extreme case can become a simple thresholding function. So this is a simple threshold function where all the values less than k, you are making it 0, and all the values greater than k, you are making it 255 or 1. So it will just give you a binary image. So this is just an example of that thresholding function here. So assuming the values are between 0 and 1, if I just choose some appropriate threshold value, this transformation function will transform in our input image to look like something like this. And later on we'll see this is used mostly for segmentation purpose. Of course, there we have to try to find out the threshold automatically using the characteristics of the input images. Right now we'll just manually choose the threshold value and try to do that. If we know the if we have the a priori knowledge about this image, and we know that okay, most of the intensity values in this image are distributed from r1 to r2, then we can manually design this transformation function. We can do a piecewise linear transformation here as shown here. So between 0 to r1, I am basically stretching by, I am mapping it to by a different. So the earlier example was just a continuous transformation function. Here it is a piecewise transformation function. So between different levels, the mapping function is different. So you can choose any one. So what it is basically doing is that if you have uh, let us say this is your input range and this is your output range. Let us say R1 and R2. So it is trying to, again, this is trying to stretch the range of R1 and R2 to occupy larger range. So in the output, the smaller range in the input is being stretched to the larger range here at the expense of compressing these two range. So the range between 0 and R1 are getting compressed, and the range from R2 to, let us say, L is also getting compressed, and the range from R1 and R2 is getting stretched. So this piecewise linear transformation function is doing something like this. So all these input values are being now mapped to a small range here. Similarly, all these input values here, they are getting mapped to a small range here, and these are getting things. So the result will be like this, because if I show the histogram of this image, you will see that most of the intensity values are distributed between this range. So if we do this, apply this kind of a linear transformation function, we'll get an amazingly improved image with with a much higher contrast and all the details very clearly visible in the image. So as last Shikha asked last time, for this we need a prior knowledge about R1 and R2, and that we will see if we plot the histogram of this image or the distribution of the intensity values in the range, we can know from that. I will talk about histogram in just a second later. But let us say we don't know, we don't want to do that. We just want to use some simple transformation. So we can use some simple mathematical functions like log and power function, and that itself that also can help us to uh, transform our images appropriately. So depending on the characteristic of the different functions, so log function, uh, so here I think most of the time when we'll apply these type of functions, we'll have to convert our image from unsigned into a double to a floating point to a double. So we'll map it to 0 to 1, and then we'll apply this transformation function. So in that case, log will take this form, inverse of log will take this function, and power, nth power will take, so if it is a square function it will take something like this, if it is a square root function it will take a form something like this. And identity and negative are simple things. So let us see some example of applying these functions on different images. So this is just a simple negative image. So this is I think a mammogram image of, so we can see the original image has, if you just take a simple negative transformation, if you do simply 1 minus r, we'll get a negative image. Negative image may be useful many times. It may be related to our perception, so what we may not be able to see in this image, maybe we're able to see more clearly in this image. And for other purposes, negative images also have some utility. Similarly, the power functions, now you can, power functions will take a simple form some like this. So take input image, raise it to some power gamma. So this is the gamma value, which we call it in popular use, and c can be some constant. So c can be some constant, depends on. And now you can have, if you change these gamma values, you can have a whole family of curves, and we can play around with this gamma, we can experiment with these gamma values to see what effect it is having in our image. So this is the same example I shown earlier. So this image was, so as you can see here, for gamma value greater than 1, uh, these are the family of curves. So these curves, what they are doing, they are basically taking a large, they are emphasizing the darker range. No, sorry, they are suppressing, yeah, they are compressing the dark range and and emphasizing the higher range, and vice versa. This one will be emphasizing the lower range values and compressing the higher range values. So so in this image, what we wanted, these details were not visible here, so we would like to enhance the darker range. So that's why we are taking gamma values which are less than 1, and we can play around with the different values. We can choose minus 6, 0.6, 0.3, 0.4, and see which one is doing the better job. I think this one is doing the, so that is that you have to just, there is a, this is just one parameter which you have to just do by hit and trial and find out the best value of that. So this is just the highlighted. So using the 0.6 gamma, the function was like this, transformation function was like this, and your resultant image would be like this. If you increase it, if you go towards the lesser gamma values, it is going to further brighten it up, and again 0.3 it is going to brighten it up more. So hopefully here I think the cavity in the this bone marrow or whatever is more visible for, so this is maybe a more useful information for the doctor who may want to do some diagnosis on that. On the contrary side, if you want to uh, this is an image which has a whitewashed appearance because of some incorrect setting of the camera. So here if you want to darken it, or here we would like to emphasize the bring it down, so we will go for gamma values greater than 1. So if we take gamma as 5, it will transform the image like this. So, and again we can play around with different values 3, 5, 4 and see which one is doing better job. So this is one way you can use power law transformation function. Another transformation function which is also used sometimes is logarithmic transformation. This is especially used um, when the distribution is quite lopsided. So if uh, I'll talk about that later. So what this log transformation is going to do, it's going to map a narrow range of low input gray values to a wider range of output values. So I hope you would have done, so for example when you do a plotting, sometimes you resort to log plot. Have you plotted any time? Have you any time used log plot? Hmm. Why do you use a log plot? So when you use a normal plot, sometimes the distribution are so close that you cannot see um, the variations in that range. So to highlight that, to stretch that range, you go for a log plot. So because when you take the log plot, so when the, for example when values are very high, let us say from 10 going from 10 to 10 to the power 6. So if you just plot it on a normal scale, then there's this because this jump is going to be so fast, you will not be able to see in a normal plot. But when you go when you take log of both side and then do a plot, then the jump then the change variations is more easily thing. So same thing is same thing is being will be done here also. So this is very useful when you go for frequency transformation. So again when we will discuss frequency components in an image. So normally the frequency when we use some transforms like Fourier transform, then what we get, the magnitude of Fourier transforms, the range is quite large. It goes from very small, from very small of like let us say 0.1 or very 0.01 up to 10 to the power 5. So for example, high frequency components can have a very large value or low frequency components can have a very low value. So the range will be very high. If you just plot it, if you just want to visualize it and show it like a simple image, you will get an image something like this. You will not be able to see the variations. What is it? But if you take a log of that and then do a plotting, or then you try to view the image, then the frequency components are more easily highlighted and can be seen. So when we discuss frequency transform at that time, we'll again revisit this. But mostly this transformation is useful for that purpose only. Um, Now coming to some other, so that was point processing transformation using some mathematical predefined functions. True that. The major problem what this was that you need to play around with some parameters to get the appropriate transformation. We'll try to see a method which is parameterless, where you don't have to manually select any parameters, which can be more automated just based on the characteristics of the intensity distributions in an image. So before we discuss histogram based method, just wanted to give us note about probability. Many times find its way in image processing. So that I hope I have sent basic review on probability and linear algebra on the group. So you all can just go through that. It's just a very short primer on probability concepts and linear algebra concepts. So sometimes we may be using those terms in our discussion. I'm not going to discuss them in the class as such. So if you just want to review them, just go through those slides. There are more detailed tutorial is available on the Gonzalez website. Of course, may not be needing that much detail of mathematics here, because I will try to abstract out most of the mathematics and discuss most in terms of conceptual level. So basically, if we can treat our intensity values as random quantities, because these values can range from, depending on our intensity distribution, it can range from 0, 1 up to whatever is your L minus 1 level. So let us say if we denote this as a random variable Zi, so any in pixel, the value of that pixel can take value from 0 to L minus 1. So so you can basically also you can estimate the probability of a particular intensity value, let us say Zk in the image, by counting that how many pixels in that image have that particular intensity value. So let us say if nk number of pixels in the images in a given image has a particular intensity level Zk, then we can say that the probability of occurring that intensity value in the image will be nk divided by total number of pixels, which is can be if m and n is the size of the image, m cross n, total number of pixels will be m into n, and the number of pixels having that particular intensity value is nk. Then nk divided by mn will be a rough estimation of the probability or the estimated probability of this random value Zk, isn't it? So so we using this thing now we can have a probability distribution function, a density function. We can calculate mean and variance in that image, and all those will help us to they will actually reflect some important image characteristics. For example, mean will give you the average intensity value in that image, and uh, variance will tell how the spread of the intensity values across that mean, around that mean. So an example of low variance and high variance, these three images with different variances are given here. So this image, what do you think should have the variance value will be high or low? It will be low, because the average intensity value will the spread around what the mean value is very less. The most of the intensity values are probably restricted to a smaller range, whereas in this image the intensity values are, you can see they will be occupying a more larger range, so that the spread will be more larger, so the variance will be high. So you don't have to visually look. So if you are developing some automated application, you can just calculate the variance of that image, and by knowing the variance value, you can know whether that image needs some contrast enhancement or not. So we will most of the time we will be using something called histogram, image histogram. You may be knowing what is histogram. The same thing is applicable here also. Histogram is basically distribution of the number of, so in case of image, if we count the number of pixels at each intensity of each intensity level and plot it, then that is your histogram. So here let us say it is going from 0 to L minus 1. and for all intensity values I'm just plotting the number of pixels at each intensity level, and this is the histogram of that image. So if you want to denote it by a function, then histogram of a particular intensity level Rk, where R is the input variable and K is the kth intensity level, is equal to Nk, which is the number of pixels having that intensity value. And if you divide it by total number of pixels, you call it as a normalized histogram, and it is basically nothing but the probability function, the PDF of that intensity, isn't it? So we can we'll see later on as we discuss different techniques. Many times histogram comes very handy in different tasks. For today, we are just going to discuss on how we can use histogram for automatically enhancing the image contrast and hmm.
Was just taking a single channel and spreading it out. But like in the histogram that we saw in the previous slide, there were two prominent sections with more. So can we have like a function which is it very like lower than higher than lower than higher? Like
Yeah, we can have it. So for that will require manual inspection of the histogram and manually designing your piecewise transformation function, and we can do that. So that we had seen that piecewise linear transformation. So accordingly, you can see. So from the histogram only, you can see okay, these are the two prominent range of the distribution here. So now you can try to stretch this range and this range at the expense of this range and other three ranges. So you can design a appropriate piecewise transformation function. But what we are going to discuss a method where you don't have to do that at all. It will automatically try to give you the best possible enhancement. So before that, so let us say if you take a simple dummy image here, and just to make you comfortable with the values of that histogram and PDF function and cumulative distribution density function and mean and variance, I'm just taking a dummy image here. So it is the outer the actual image is 100 by 100 size, and most of the outer pixels have intensity value 10. The middle one of the 60 by 60, except this 20 by 20, have 20, another intensity value 20, and this 30. So what will be the histogram of this image will look like? So let us say our intensity values R is taking some values from, it is taking 10, 20, 30. Of course, there will be some intermediate values also, and it will go maximum to 255. Now what will be HR? HR is the histogram that we have, HRK. So for 0, what should be the histogram value? There is no intensity value 0 here. So before 10, there are all they will all be zeros. At 10, how many? So before 10, let us calculate for 30. 30, how many are there? So there are 400 here. Sorry, so the mapping is not. For 20, and for 10, 6400. Huh? So you can subtract accordingly, and for the remaining, it will all be 0. Sorry, it's not. Some will be obviously 10,000. Now, if you want to uh, calculate the probability values, the PDF function, what it will be. So for 0 0 it will be 0 0. For 10 what it will be, divided by 10,000, so it will be 0.64. For 20 it will be 0.32 and 0.04, and these all will be 0. See, what about the, the CDF or the cumulative distribution function? CDF is the cumulative distribution, so you just have to integrate from 0 to up to that intensity value. So here it will all be zeros. We are going to use this CDF function later on, so that's why I'm. So it will be 0.64, and intermediate values it will all be 0.64. At 20 it will become 0.96, and it will remain 0.96 up to 30. At 30 it will become 1, and then it will remain 1 for the remaining. So here the sum was sum of PR, all probability values obviously will be 1. So how do you calculate mean? How do you calculate mean? So take that particular intensity value RK, multiply by its probability, and sum it for all intensity level from 0 to L minus 1, and you can calculate this. Should I calculate it? I think so. This bit will be 10 times 0.64, 20 times 0.32, plus 30 times 0.04. So this will be something around, I think it will come around 14. And what will be sigma? So what is the formula for variance? Variance is sigma square, and sigma is your standard deviation. So how do you calculate variance? PRK times RK minus mu square. So, and you can calculate this value. So this will come out around, I think sigma square will come around, I think 32, and be around 5. The variance standard deviation will be around 5. So we will be using this sigma and variance many times. So just so so coming to this, the method that we are going to discuss about is called histogram equalization, which will help us to automatically enhance this the contrast of a given image. So this is an image which looks quite good in its contrast, and if you plot it to histogram, so in the function in MATLAB, if you are using MATLAB, you can just use the function hist, give the input image I, and it will return the histogram, and you can just I am show that or display that image. Um, this is an image which doesn't has a good contrast. All of them are, you can see all of them are looking towards dark, and if you plot the histogram, which is clear that most of the intensity values are spread in the darker side. So I'm plotting from 0 to 1 here. Similarly, this is the opposite end of the image. So all the images towards the brighter side, and again the intensity levels are occupying the white range. This one is taking somewhere in between. The intensity values are taking somewhere in between, and this is an image which has a good contrast. As you can see, it is using the all the range from 0 to 1, and you can see the distribution is almost flat or evenly distributed. So this is just the these all 4 images that we have seen, same image, same content with different contrast, One was a more darker image, one was a brighter image, this was a low contrast image, and this was a good high contrast image, which would like ideally like to have it. So if you are given any image, what should we do on its histogram so that we can get this an enhanced image? We should try to spread out its histogram so that it uses all, so that it basically is, it uses tries to use most of the range in their in your level, as well as they are also, rather than having a random distribution, all of them are almost more or less flat or evenly distributed. So if we can know, if we can do this automatically, then we don't have to play around with any parameter. If we so how do we get a histogram? We know how to calculate the histogram. We can get its uh, we can normalize it and get its probability function, PDF function. Now how should we change this PDF so that we automatically, so that we can get this? So that is our task. We want to do contrast touching. Our task is to take an input image, obtain its histogram, normalize it by the total number of pixels, and that will represent, and that will be basically its PDF function. And now we will try to derive a transformation function that will give an output image PDF function, which is more or less a constant function, because we have seen if you get a histogram which is almost flat, evenly used across all the range, then it will be it will have a good, sorry, yeah, so it will have a good um, it will be a kind of an enhanced image. So this is our target. Our input image can be any random image with any random probability distribution function. Our output image we want, for the output image we want our PDF function ideally to be something like this, to be a flat PDF function. So what mapping can we do, which we can take this input PDF function and get this output PDF function? Any idea? Okay, you will have to do some derivation. It is not so straightforward. To do the derivation, I am going to assume one thing at least on the transformation function, that the transformation function I am going to use, it will be a monotonically increasing function. And why you would like to be, so it can be either strictly monotonically increasing as this, or it can be like this function where multiple values may get mapped to a single value, but never there is an inversion. So if we don't allow monotonically increasing function, then if you have a function, if you have a random function like this, then it will be a problem, because a higher value intensity value may get mapped to a smaller intensity value, which will cause an artifact in the image. The content may get changed, because we won't like would like to do that. If 10 is getting mapped to 20, then 15 should get at least mapped to 20, or possibly greater than 20, not less than 20. So we should ideally our TR, our transformation function, should be a monotonically increasing function. And ideally this transformation function will the output range, so the input range is from 0 to L minus 1, the output which is S value, because S is equal to your TR, S value should also range from 0 to L minus 1. You should try to use the entire range from 0 to L minus 1. So these are the uh, assumption that we'll make on the transformation function. So now if our task is to take this any arbitrary input PDF function and get this output PDF function, what should we do? So if our transformation function S equal to TR is a monotonically increasing function, then, so let us say for any arbitrary value here, Let us say rk is getting mapped to some value sk in the output. Let us say this transformation function tr is going to take an intensity value as rk and is going to give some intensity value sk. So now what is same in these two graphs? What will be same in these two things? So why I'm plotting this? So in this image, why I'm choosing this value 1 by L minus 1? So the range is from 0 to L minus. So L is the max. L is the total number of levels of intensity levels. So that's why I'm going to go from 0 to L minus 1. Why I'm taking 1 by L minus 1? I want a constant PDF function. And why? So why it should be 1 by L minus 1? Should be same and sum should be equal to 1. Sum of all probability values from 0 to L minus 1 should be equal to 1, and ideally we are what we want, ideally we are wanting a constant flat, so that constant value will be 1 by L minus 1, because then when you integrate from 0 to L minus 1 it is going to be the sum of all probability values is going to be 1. So that's why that constant value that we want is 1 by L minus 1. Is that clear? Okay, now what is same here in this image and this image? What is constant here? So all the pixel values, if pixels having value rk is getting mapped to pixel value sk, all the pixel value less than rk are going to map where? Less than sk, isn't it? So pixel values from 0 to rk, all the pixel values from value 0 to rk are going to map from pixel in the range from 0 to sk, not greater than sk. So what should be the same? Range is same, but the count of the number of pixels in this input image having range from 0 to rk should be same as the count of the number of pixels values from 0 to sk. So that means the area under this curve till rk and the area under this curve till sk should be same, because that area is going to give the total number of pixels, because this is the PDF function, this is the histogram, a normalized histogram. So the count of the area under this, if you integrate it from 0 to rk, that area is going to give the total number of pixels values from 0 to rk, and similarly the area under this will going to give the total number of pixel values from 0 to sk, and this area you can equate it because that is going to be the same. So what is this area in the left hand side? 1 upon L1 mass into sk. In right hand side, what is this area? How we will get the area? Isn't it? So of course here we are representing it as a continuous function, but in our case we are going to have a discrete function. In an image we are going to have a discrete, so this integration will change to summation. So I'm just going to show you the final thing. So sk is equal to tr. So our transformation function will be, so here if you see this implies sk is going to be L minus 1 times integration will change to summation prk from 0 to, so this should be pr only. So I think the notation I'm taken from the book. So this is what I'm doing, the taking the input PDF property function PRR, where RJ is going to go from, why it's going from 1 to k. So, but I think there's some problem with the notation. So the notation in the book will be something I should be 0, because the 0 is the first level. I'm not just I'll verify it from the book, but it will go from 0 to k. That is the area from the left hand side curve multiplied by L minus 1, which was basically this L minus 1 was a numerator here, so it went to there. So this thing is going to be the resultant transformation function. The transformation function that we wanted will be nothing but this. This this thing is nothing but your CDF function, cumulative distribution function, what we calculated earlier. So to get this transformation, you don't have to do anything. Calculate its histogram, calculate its PDF, calculate its CDF. Once you get the CDF, just multiply it by that constant L minus 1, and you will get the output intensity values. So the transformation is very simple, nothing nothing much. Even in implementation, it's just a small line of code. Just count the number of input image, count the distribution, calculate the CDF function, and then multiply with L minus 1. So I've just substituted the PRAR here as by NK by total number of MN, but that remains the fact here. So if you apply this transformation function, let us take this input image. I'm just showing you the result here. So this image which was towards the darker side. So if you calculate from the previous formula our transformation function, the transformation function would come something like this. And using this transformation function, if you map to output, as you can see, this transformation function is going to take all these values from this to here, because I think all the values are distributed from here to here, and it is basically automatically stretching it to the entire range. And although we are not getting the ideally flat one, because this is a approximation what we are doing here. It's not a continuous PDF. It's first of all it is discrete, and then again when we do discretization, then again we have to do rounding off when the intensity values will not get mapped to exact value. So if then you may output value may get 5.5, then you have to either round it off to 5 or you have to round it off to 6. So because of that rounding off error and all that, you will not get an ideal flat PDF here, but it will be close to a flat PDF. And if you see this image will be the enhanced image. And irrespective of what input image if you take, if you apply that formula, you will get different transformation function. For the first image, you will get the transformation function this. For the second image, you will get the transformation function this. For the third image, where the intensity values were in between, you will get a transformation function like this. The fourth image, which was already enhanced, the transformation function will be almost near to identity function. So that means you don't have to visually know the image. We don't have to play around with any parameters. Just do that function, do the transformation. So it is fully automatic in that sense. It doesn't has any parameter. It will automatically end up in the same image or almost same image with almost similar output PDF. Any question till this point? So there is I will not discuss an example just to practice by hand. So using a demo image, a dummy image of with a particular distribution, you can actually calculate it out by your hand. What I'll do is I'll demonstrate it in MATLAB. This whatever we have discussed here, little bit. So first I'll show you the gamma function. So I'm reading some image. First of all, I'm just trying to multiply it by a constant scale factor and show this image. So I've tried to, this is the original image. Here now you can see the difference. Actually that IM show itself was adjusting it back. Whatever change you are trying to do, it was readjusting it back to the original thing. So this is just trying to brighten up the image. This is not a contrast stretching function. This is just a brightening scale. For if you want to do the contrast adjustment, then we said that we can use a gamma power function. So if we take a gamma value of 1.5, raise it to power gamma and then show it. So I've taken two gamma for 1.5 and one is 0.5 and shown the two images. So this one is going to emphasize towards the darker, and this is going to shift towards the lighter one. But this is more a contrast stretching thing. And there is an inbuilt function IM adjust, which will automate where instead of doing all this, I think this is just one function for power function, gamma, and all those things. You can just provide some parameters here, and it will automatically do you the corresponding adjustment. Another thing I just want to show you your histogram thing. So for histogram, I'm using a reading of image, showing the image and its histogram. So IMHist is the function I think which gets the histogram of the image. So this is the image where the child is doing some pouting here. So as you can see, the intensity values are in a small range, some middle range. So this is a good image to try stretching the contrast. So you can use IM adjust function itself, and you can specify. So the you can, if you know the intensity original input range are from 0.3 to 0.6, and you are trying to stretch it to output from 0 to 1. So that is one method. Other method, you can use the histogram equalization method itself that we have seen. You can implement it, or there is an inbuilt function, and you can see the output of both. So this one was by where I was just doing the piecewise contrast stretching using the specifying the range. So as you can see, it has stretched the contrast to entire range, but it has not made created a uniform flatten it. It has just stretched it as per things. So you can see some improvement here. But histogram equalization has also not only tried to stretch it, but also tried to flatten it out. And I think the result may not be, but I think you can see some differences here. The more details are available here and then there. So histogram equalization, as I said, is a will most of the time will give you the good result without playing around with the factors. So should we stop here?